Hello students, this is my second video lecture on IR spectroscopy for Sem-V students. I am Dr. Parin Sheikh from LG Institute of Applied Sciences. Now in the previous video lecture we have discussed basics of IR spectroscopy, and now in this video lecture we are going to discuss different factors that affect the IR frequency. Okay, now first, to go through or to understand the theory, here we have to learn some basic key points. That means first, that is higher the force constant or stronger the bond, the higher the frequency or wave number. Here we can say, we have to remember, as the force constant increases, the frequency also increases. Second, the size of the atom is small, the frequency wave number will be higher. Or we can say, size of the atom decreases, the frequency of wave number increases. That is second key point. Third key point, the broadening of OH bond absorption due to hydrogen bonding. Here hydrogen bond that is broad due to there is OH bond absorption. Fourth, electronic effect can also affect the frequency of a functional group. Here electronic effect in terms of resonance and inductive, as the plus R and plus I effect, which decreases frequency of wave number. Here we have to remember that if there is plus R and plus I effect, which will decreases the frequency. If we have minus R and minus I effect, which increases frequency. That thing we have to remember. Okay. Now the following factors. Now what is our theory? That is different factors affect to IR frequency. So here some factors that affect the IR frequency. First, that is force constant and reduced mass. Second, that is hydrogen bonding. Third, that is electronic effect. Fourth, that is Fermi resonance and overtone. And fifth, that is ring size. In this video lecture, we are going to discuss first three different factors. First, that is force constant and reduced mass. Now, how the force constant and reduced mass affect the IR frequency? We can understand this by taking one equation, that is Hooke's law. According to Hooke's law, the wave number, or we can say frequency, is directly proportional to K, where K is the force constant. Or we can say as higher the force constant, higher, or we can say stronger the bond. Triple bond having higher force constant compared to carbon-carbon single bond. And the wave number is inversely proportional to mu. Mu, that is reduced mass. Okay. Reduced mass means we have to decrease, or there is lighter atom. Lighter atom. So we can hear the conclusion is that the wave number is directly proportional to K and inversely proportional to mu. Now we are going to discuss some factors according to Hooke's law. We can say from the Hooke's law, we can say that the higher the force constant or stronger the bond, the higher the frequency or wave number. Here we have to remember that force constant is higher or there is stronger bond, which will increase the frequency also. Let's take one example. Here we are taking carbon-carbon single, double and triple bond. Okay. Carbon-carbon triple bond, that means its bond is stronger compared to carbon-carbon single bond. We can say it is weak bond. So what now? It affects the IR frequency as stronger bond means higher frequency. Weaker bond, that means lower frequency. That we can understand by the taking of this data. Means in this following table, as the carbon-carbon single bond having frequency lower compared to carbon-carbon triple bond. This is due to if we have to apply more force or the force constant is higher, we need also the frequency higher. Second, that is according to Hooke's law, we can say that size of the atom is small, the frequency or wave number will be higher. Here, if we have decreasing the size of the atom, the frequency becomes high. Okay. This can understand by this example. Here, CH bond, CD bond, deuterium is replaced by fluorine, chlorine and bromine. So we can say that here we are taking heavier atom bonded to carbon, and CH, that means lighter atom bonded to carbon atom. Now what will affect to frequency? Here, as the atom become heavier, the frequency will be lower, and as the atom is lighter, the frequency is higher. Okay, now why this happen? Because higher frequency is depends on vibration of the molecule. If we have carbon hydrogen bond, so they are lighter atoms. Hydrogen is lighter atom compared to bromine atom attached to carbon atom. So carbon hydrogen bond can easily vibrate than carbon bromine bond. So as the vibration is more, the higher frequency will also higher. This can understand by the following table. Okay, in which carbon hydrogen bond having higher frequency compared to carbon carbon bond. Now the second factor, that is hydrogen bonding. Okay, now hydrogen bonding brings about remarkable downfield frequency shift. As the hydrogen bonding is there in our compound, so the frequency will be lower. Now we know that stronger the hydrogen bonding, greater the absorption shift, and which decreases, or we can say lower the wavelength. Now there is two types of hydrogen bondings. First intermolecular, second intramolecular. Okay. Now OH non-bonded, or we can say pre-hydroxyl group of alcohols and phenols absorb strongly in the region of 3584 to 3700 centimeter inverse. Here we have to remember normal OH frequency we will obtain in the range of this. Now let's take one example, that is orthohydroxyacetophenone and para-hydroxyacetophenone. This is structure of orthohydroxyacetophenone. In case of orthohydroxyacetophenone, there is intramolecular hydrogen bonding shown in here. It is shown. Now, due to hydrogen bonding, we get broad band peak in the range of 30-77 centimeter inverse broadband. Normal it observed around 36 centimeter inverse, but due to hydrogen bonding, we get band at lower frequency. Now we have another example, that is para-hydroxyacetophenone. In case of para-hydroxyacetophenone, we observed the band in 3600 centimeter inverse, which takes in diluted CCl4 solution, means we get normal band. Why this happen? And also we get sharp band. Here intramolecular hydrogen bonding occurs, but the concentration is very low compared to intramolecular hydrogen bonding. Intermolecular hydrogen bonding has lower concentration, so we can get the sharp hydrogen, or we can get sharp peak. Next another example, that is of carboxylic acid. In case of carboxylic acid, there is formation of dimer. Here dimer of acid is formed. So monomeric form means if there is single structure of acid, or we can say one monomer of acid, we can get free OH stretching near 3520 centimeter inverse. But here formation of dimer. So due to dimer formation, the higher frequency decreases to range 2500 to 3300 centimeter inverse. This is due to there is formation of OH bonding, right? Here two OH bondings are there. So we get very broad peak in the region of 2500 to 3300 centimeter inverse. Okay, now why we get the broad peak? We get broad peak due to separation of charge. Here where charge separation that brings polarization, and due to polarization we get broadband in case of OH frequency. Next third, that is electronic effect. Now replacement of an alkyl group of a saturated aliphatic ketone by heteroatom shifts the carbonyl absorption. Either it can shift carbonyl absorption to lower side or higher side. Now next, the direction of shifts depends on whether inductive effect or resonance effect. Here we have to consider inductive effect as well resonance effect. Okay, now inductive and resonance effect are of two types, that is plus R and minus R, and also plus I and minus I. Plus R means we are taking groups such as OH, NH2, etc. Minus R means we have NO2, COOR, etc. Okay, plus I we are taking the group, we can take the group methyl, ethyl, etc. Minus I we can take chloride, okay, any halogen atom. Okay, now as we discussed earlier that plus R and plus I enhance the frequency, minus R and minus I decreases the frequency. Here there is one example, or we can say here resonance is shown. Okay. And it is inductive effect. First effect, that is resonance, and second, that is inductive effect. In case of resonance, heteroatom having lone pair of electron which donates to X C bond and the carbonyl C double bond O, which gets converted into single bond. Okay, here C double bond O gets converted into CO minus. Due to that, the frequency will be decreases. And in case of inductive effect, R provides 2 electrons to carbon and carbon provides electron to X. Okay, now for example, the introduction of alkyl group to produce plus I effect. Now here we are taking example of plus I effect. In case of formaldehyde, acetaldehyde and acetone. Formaldehyde having HCHO group, acetaldehyde having, we are replacing hydrogen by methyl group, means we are increasing plus I effect. In case of acetone, we are replacing second hydrogen of acetaldehyde by methyl group. So here we can see the frequency continuously decreases. Okay. Why? Because we are enhancing plus I effect. Now let's take the example of minus I effect. Here we are taking example of acetone, chloroacetone and tetrachloroacetone. Here the frequency increases. Why? Because we are inserting or we are putting minus I effect. Acetone, in case of acetone, we are taking 1 chloride atom, and in next we are taking 4 chlorine atoms. So it will increases the frequencies. Okay, sorry, here C double bond O gets converted into CO minus. Now next, that is resonance effect. Here in case of resonance, first example in which NH2 is there, NH2 showing plus R effect, which donates its electron to bond, and via resonance C double bond O that gets converted into CO minus. So it will decreases the normal frequency of C double bond O carbonyl, that is 1700 to 7600 centimeter inverse, and here we are getting the frequency that is 1677 centimeter inverse, and that is due to C double bond O gets converted into CO minus. The next example, here we are taking minus R, NO2. NO2 shows minus R effect. Minus R effect, so it directly take the electron from C double bond O. C double bond O, and C double bond O gets converted into C triple bond O. So here C triple bond O, that means force constant is increases. So we are observe that the frequency is enhancing to 1700 centimeter inverse. Remaining example is paramethoxyacetophenol and phenyl acetate. Now, okay, further factors we will discuss in our third video lecture. Thank you.